maybe we will have time to do it. And so this is a very simple thing. So it's something which comes out with a thing which is called Graham-Schmidt orthogonalization. And it's used not only in the linear algebra, but also in functional analysis. So what is it? So if you have a if you have a V, right? So linear space, and it's a span. So it's linear span of vectors A1, AN. And so then you might be interested. So this A1, AN, it's a form, maybe kind of, so it's a kind of, we can form a basis. So of the, so you can assume that we are linearly independent. But they might be not orthonormal basis. So in this case, you might be interested in building a orthonormal basis from A1 and AN. Or more generally, you can have something which is called a flag. Right? So a flag of linear spaces. So you might think about that it's important that it's A1, then after that A2, and after an A. And so this is basically that you have something like a V1, space V1, included in the space V2, included into the space so on, included into the space Vn. So in this specific example, it would be something like Vk is just a span of A1, AK. So, and you want to build a orthonormal basis such that the first element Q1 would span V1, Q1, Q2 would span V2, and so on. So we would like to have an orthonormal system. So Q1, UN, so that Vk would be equal to the span of Q1 and Qk. And so that's the task that we want to do. And so the kind of a Gram-Schmidt orthogonalization process is just a process how to build this. A very natural thing. So you just kind of, so this Gram-Schmidt. So again, so this is come more from functional analysis. So kind of Schmidt worked not on the vectors, on the functions. So, and basically there was a functional spaces, and he wanted to build kind of a orthonormal basis in these spaces. So he worked with functions. And so, but it's basically the same thing. So how you can build it? So you start with building Q1, right? So this should be this should be proportional to A1 because it's a basis for V1, and V1 is spanned by A1. So you said that this is equal to A1, right? So with some coefficient, right? So it's equal to A1. So now you need to choose the coefficient, and Q1 it should be have a length 1. So it's a first element of the orthonormal basis. So you just need to divide by the length of A1. So you divide by the length of A1. So A1, no. And so now after that you have a say something like you're doing something like this construction. You have something like a v k minus 1, right? And in this vk minus 1 you already choose the basis, so you have a basis q1, so 2, so on, and qk minus 1. So in this vk minus 1 you already have a basis, right? So what you want to do is kind of you have a vk, which is this vk minus 1 plus additional vector ak, right? So this additional vector ak, and so instead of this ak you want to add additional 1, right? You want to add additional qk. Right? So, and it's clear how to do it. You'll need to project ak on the ak minus 1, subtract the projection, it will be kind of, so this will be kind of some vector perpendicular to vk minus 1, and normalize it. So that would be it. So for example, so let us do the first step. So how we could do the first step, and his so not the first, second step here. Okay? So the second step would be something like that. Okay? So you have here, so v1, right? So some vector q1 here, which is already computed. So here you have a a2, and you'll need to build a vector which is perpendicular to, so which would be in the same plane as a2 and q1, which would be perpendicular to q1 and have a unit length. So for this you just project a2 on q1, and so you project a2 on v1 and subtract it from a2. So this, so you need to subtract from a2 this projection. So okay, so q2 will be equal to first one, and after that we'll normalize it. So it would be a2 minus the projection of a2 on v1. So we'll need to kind of just recall back how we do the projections, right? And so this is kind of easy. It's just kind of, you take scalar product. You take a scalar product of a2 with the basis vectors, with orthogonal basis vectors. So in this case, it will be a2. So this is orthonormal basis. So it's a2q1, so scalar product, and multiplied by the vector q1. Okay, so now this is a kind of standard formula how you project on the line. Okay, so in the line spanned by the unit vector q1. Okay, so all right, and after that you'll need to divide by something. Okay, so now instead of this q2 is equal to, so maybe kind of me write it slightly differently. Maybe me write this way. So in two steps, let us call it v2, and after that q2 would be just equal to normalization, v2 divided by the norm of v2. So this is the first step. Okay, so it's pretty crystal clear how we do it. And after that, we just generalize it and kind of write. So if you want to calculate the qk, then first of all, you take you calculate VK, so which is proportional but not necessarily unit length. So you take AK new vector, right? So this new vector, project it on the space which is below, and for this you'll need just to remember how to project on the plane which is spanned by orthonormal vectors. And this is just formal like that, so you can check it that we did it before or something like that, so you just kind of figure out that this is the same. So it's AK minus, and here will be AK product with Q1 dot product with Q1, scalar product with Q1 multiplied by Q1 minus AK product with Q2 multiplied by Q2 minus, and so on. Final is AK QK minus 1 QK minus 1, and that's it. So this is a projection, right? Orthogonal projection of vector AK on the previous space on VK minus 1. So this is a AK minus this projection, so it's perpendicular to the space. So it's perpendicular to, in particular, it's perpendicular to all Q1, Q2, and QK minus 1. It can be also checked kind of formally. You can just multiply and check it by Q1 and so on, right? And so the last thing is we'll need to normalize to make sure that this is unit vector, and so this formula can be used before. So Q K is equal to VK divided by VK norm, right? And so on. So you can continue this process and clear that always when you generate new vector Q, it will be perpendicular to all the previous one, right? So again, so very easy to check because you just take QK, so VK, and multiplied by AK, multiplied by 1 over QI with a smaller n, kind of, you will see that these things becomes equal to 0. And so just kind of from this formula immediately can be verified. Okay, so this is algorithm. It's called Gram-Schmidt orthogonalization. Orthogonalization. Process. Right, and okay, so in the book in the Trefethen book you can see that it can be also applied to functions. Right? So if you define the scalar product appropriately, so norm of the functions appropriately, then you can do it also in functional spaces. Okay, so this is a kind of chapter. I'm just keeping it because it's not what very interesting for us. Okay, so now what about QR? Okay, so here we have a Q1, Q2, QK calculated in terms of the vectors AK. Okay, so can we write it our way around? And so we will get here something like that. Let us just rewrite this, but in terms of what is AK in terms of in terms of vectors QK. Right. So we write it like that. So we write it A1 is equal, and let us call this thing R11. Right? So it's equal to R11 Q1, where we in general define this K, right? In general, it will be defined as this norm of a vector V in this algorithm. So it will be some numbers, kind of. So if you can do this, so the point is that you did this Gram-Schmidt organization. At each point you calculated something, right? In particular, you calculated at some point you calculated this the norms of this thing, so they already are available. So some numbers, so I call them. So this RKK will be called this V, something which I called previously VK. I use QR, so I need R, so this will be R. And so and this is in terms of the previous algorithm. So somebody ask something. Oh, okay, somebody, all right. Okay. Okay, somebody, yeah, somebody, this is the problem. Somebody kind of didn't got my message about that we have online. So yeah, so you, yeah, so, okay. All right, so this is okay. And so we will probably be online all this. Well, we will be online all this week. So probably your exam also be online. This will be later. Okay, so this A1 is equal R11 Q1. Right, so now what about A2? Right, so we'll write it. A2 is from here. Right, so A2 is equal to Q2. So this is V2 plus this thing. So V2 is equal to this Q2 multiplied by V22. So it's equal to R22 multiplied by Q2. Okay, so this becomes V2 and plus this thing, and we call this thing R 1, 2, I think. Okay, so let me, I'll check it. So this should be, yeah, R1, 2. So plus R1, 2, Q1. Okay, so where, so here's R21 will be just equal to, no, it's should be, yeah, R12 is R12. It will be equal, in this case, this A2Q1. This color product, which you also kind of probably calculating during the running this algorithm. Right. Okay, and more generally, so we define R ij as similarly, so it will be A J Q I. Right. So now, and this is all when we calculated, it was also this I was smaller than J. Right? So in everywhere where we calculated, this coefficient on Q was smaller than coefficient on A. So this I was smaller than J. So this is defined when I is smaller than J. Okay, smaller than J. Yeah. So this is a diagonal elements, and this is if it's I smaller than J, and this is upper diagonal elements of some matrix. Okay, so it will be 0 if I is greater than J. So this is a lower diagonal elements of this matrix R will be equal to 0. So it will be upper diagonal matrix. So now, okay, so and after that we can in general write kind of a general formula. The general formula will look like that. It will be AK is equal to RKK QK plus RK K minus 1 K QK minus 1 plus so on plus R 1k q1. So this is a general form, and what I claim that if you have a matrix A which have a columns A1, A2, and so on, AK, then it's equal to the matrix Q, right, with the columns Q1, Q2, Q, so his n maybe finding n. This is general kind of, but in principle up until n. And so Qn, so these are columns multiplied by R, and this is R. We'll have this coefficient, so it will be R11, R12, R21, sorry, 13, so on, R1n, here's R22, 0, R22, R23, R2n, here's 0, 0, R33, and so on, R and n. And you can verify that this is true. So for example, A1, and so it's just kind of from one of the interpretation of our multiplication. So if you multiply this matrix over first column, so this matrix, so the first row, the first column here is equal to the matrix here multiplied by the first column here. And so the first column here multiplied by this matrix is just the columns of this matrix taken with the coefficients which are given in this column. So this is equal to R11 times Q1 times column Q1, and this is exactly this thing. So this is kind of, now if you look at the second column here, the second column is equal to this matrix multiplied by the second column here. Right? And what it is equal, it's equal to linear combination of Q1 and Q2 with coefficient given by the R12 and R22. Right? So it's R12 multiplied by the first column here plus R22 multiplied by the second column here. And this is exactly as here, kind of is written here. And so you can just verify it, maybe kind of briefly explain, but you can verify it. Are you asking a question? No? Matthew?
No, I don't have a question.
Huh?
I don't have a question. I wasn't asking.
Yeah, okay. All right. Okay. Now that's it. So this is A, this is Q, and this is R. Yeah, so this is a call QR. So you from the construction, when you see that this is upper diagonal, well, you can also see that here that these elements R11, R22, R33, they are norms of a vector. So they are all positive. Right? And also maybe one word to say, well, it might break at some point. Right? So when this algorithm can break, when you cannot divide by the norm, so when the norm of a vector is equal to 0, this will happen only if you add some new vector ak, and it's inside the previous linear space. So if the ak here is inside the vk minus 1, then this new vector v2, and so this ak minus the projection, it would be equal to 0, so this would break. But this would mean that ak is a linear combination of the previous vectors. This would mean that the matrix A is not full rank, or it would mean that the flag is not increasing at some step. So the flag of the subspaces should be increasing right? So it couldn't be that at one step you edit a vector and stay the same. So the upshot that if A is full rank, then you can always write down this decomposition. So this is a this is a kind of a proof theorem which we could formulate from the beginning, which says that if a matrix A is a full rank matrix, then, and maybe I'll kind of formulate it, when there exists a QR decomposition where Q is a matrix with perpendicular columns, with orthogonal columns, and R is the upper diagonal matrix with the diagonal elements which are positive. So let me write it down. So this is a theorem, and this is kind of algorithm how you can build this, decomposition. So effective algorithm for proving this. In fact, it's possible to prove that this is a unique decomposition, right? So there is no other way, kind of than to do it like this. So theorem. So that A, B, M times n full rank matrix, and here for simplicity we assume that M is greater than or equal than n. Then there exists a unique decomposition so A is equal to QR. Right? And so here's I'm following that the thing which is kind of written in the with 3 book. So he kind of so puts this symbols here, carets here, because he thinks about it as a reduced decomposition. So this is not a square matrix, not necessarily a square matrix. So so it's called reduced QR. He calls it reduced QR decomposition. And so a unique decomposition QR where Q is an M by N matrix with orthonormal columns, and R. So again, with this symbol, caret is n. Okay, so he's n times n, so it's a square matrix, upper diagonal matrix with so diagonal elements are I, which are positive. Which are positive. This is a reduced QR decomposition. So if for some reason you want to make sure that this is Q is orthogonal matrix, so you need to make it square. And so you can kind of increase this matrix and change R such that this increase doesn't matter. And so this would be called the full QR decomposition. So you can make something like a matrix like that. So this is a kind of N. Right? So this is M. Right? So this is this Q. Right? So you can put here something new, kind of such that the matrix would be still have orthogonal columns. So this would be matrix Q. So it would be M by M matrix, right? And so to make sure that this doesn't matter, you would make R like that. So R would be, okay, so this would original R. So R11 is R and N. And here you just add the block of zeros, right? Totally zero elements. So this, whatever is here is not means. And the dimension would be M times N. And this would be R. And so this is a R tilde. So you add something here and zeros here. With something you can add new column vectors to ensure that the resulting matrix is orthogonal. So this is orthogonal. And this is still upper triangular with the diagonal elements equal positive, right? So so still upper diagonal. So you would call this as a full QR decomposition. But I don't see what's the kind of well, this is not much kind of interest in this. I don't see, at least I don't see kind of what's the kind of big point of this kind of thing. So now if the matrix, original matrix was a square matrix, then there is no difference between reduced and full decomposition. So I think that usually kind of when you talk about QR decomposition, you talk about reduced QR decomposition, and full QR decomposition is of course not unique. Kind of you can do it in many ways. You can add this vector. Well, might be not unique. Right. All right. Okay, so this is a QR decomposition. So what is the use of it? So now kind of, so it's a part, usually it's a part of the algorithm. So one way where it is useful is in the linear regression, kind of, right? So it's just kind of apparently fast method to solve the equations for linear regression. So application to linear regression. So remember what we have a linear regression. So at least in some form, you could write something like that one. You can write so let me see, kind of a changing notation. So here I use this one. So linear regression. So you can write that you want to solve the equation AX is equal to Y. So this is dependent variables. So we have it M times 1. This is a matrix of the coefficients. So it's N times 1. This is a data matrix, kind of, if you interpret it as a linear regression in the statistics. This is a data matrix. Now I call it A. And this is M times N matrix. And so it's, okay, so M observations on N variables. And these are coefficients, N coefficient for the variables. So you want to fit kind of this regression. It is usually not possible because the number of the coefficient here is N, the number of the equations is M. Right? So it's hidden here as a system of equation, M equation, N unknowns. So if m is greater than n, then you cannot solve it. So the solution, so linear regression solution says, well, let us do it approximately. Let us look for epsilon. Okay, so let us allow his epsilon and find x so that norm of epsilon was minimized. So sum of the squares of the epsilon should be minimum. So you choose this x. So what is known is a is known, y is known. So you choose x such that when sum of the norms is so this was how kind of formulated, right? So and after that we saw this is easy to solve. It actually reduces to solution of the normal of equations. So normal equations. So it's kind of it's like if you multiply by a transpose on the left here, a of x, and it's equal to a star y. So now this is okay. So this was m by 1, right? So this is was matrix m by n. So but after multiply, so this is n by n matrix. Right? So this is n by n 1 vector, and this is n by 1 vector. And so now you have this is a number of the equation is n, number of the coefficient is n, so it's solvable. Right? So and kind of at this moment we stopped and say, all right, so you can solve this system of equations. That's it. So well, QR is sometimes used to solve the system of equations more efficiently maybe than other methods. And so how it works? And so you just write down the so somewhere behind this, the idea is that you do a projection. Right? So that's why kind of it's useful, because you are doing a projection on the column space of A. And so QR allows you somehow. So the idea is why kind of it's useful is that it allows to project. And if you know the orthogonal basis, then it's very easy to project. Right? But formally, what we are doing is kind of we're writing, okay, so let us write QR, let us compute QR decomposition for A. So A is equal to QR. Right? And it's reduced QR decomposition, it doesn't matter, it can be reduced. Right? So I don't put here these things, but I mean reduced decomposition. So this is n by n, this is m by n matrix. Okay, so after that, let's plug in it in this equation. And so what we'll get. So R, so again, so I stop writing these carets here. So R star Q star multiplied by Q R so X, and here what we'll have here, we have R star, so equal to R star Q star Y. Right, so one thing is we kind of immediately look here, and it's tempting to write down his identity, right? Because it's Q star Q, and it's actually his identity. Right? So sometimes you know that this is not a square matrix, so you'll need to be cautious, right? So in one direction, it's identity, Q star Q is maybe identity, Q star not identity. So you'll need to be cautious and check. So, but here, remember that this is kind of Q is a kind of matrix with columns, which is a Q1, Q2, Q so on, so Qn, which is orthogonal, right? So if you calculate this thing, you'll take a Q1 and multiply by other vectors, and the result kind of will be equal to 1 or 0. Right? So if you look at this attention, you can get convinced yourself that this is actually identity matrix. And so Q star maybe not, but this is identity. Right? So it's the right direction. So this is an identity matrix. So in what its dimension? So this was m times n. So this is n times n identity matrix. Right? R here is also n by n. So now you can rewrite it and write it. This is R star R X is equal to R star Q star Y. Right? Now, okay, so another temptation, right? So you have here R star and R star. Right? So it's kind of natural thing that maybe you can kind of remove it. And indeed you can. Right? So this is because, well, what you need to check that you can multiply by R star inverse on both sides. Right? So on both sides on the left, if you multiply, you can remove this. So you need to check that this R star minus 1 exists. Right? But first of all, this R, first of all, it's square matrix. It's n by n matrix. Kind of it's reduced decomposition, so it's n by n. And after that, you will see, well, this is an upper diagonal. Right? So it's upper diagonal matrix. Right? And elements on the main diagonal are not 0, they're greater than 0. So, well, you can check that this is invertible. For example, determinant of this matrix, product of the diagonal elements, it's positive, so not 0, so it's invertible. So this thing exists, right? Exists. So you can take and multiply this equation on both sides by R star minus 1, and you'll get another kind of step. You'll get that Rx is equal to Q star Y. Right? And now kind of the idea is that it's once you calculated QR decomposition, then if you know Q and R, then this is just one multiplication of the matrix Q by Y, right? Which is easy kind of to write down. Right? If you know the columns of this matrix Q. And this is just a solution of a tridiagonal system of equation, which is also very easy. And so because you will have something like that, R11, something like R11 X1 plus R12 X2 is equal to something, then will be something like R. So in case of if it's 2 by 2 matrix, so you can, I'm illustrating. So R22 multiplied by X2 is equal to something. So from the lowest equation, you immediately kind of find out what's X2. Then you plug it here, kind of remove, and you can immediately find X1 and so on. So this is very easily solvable equation by substitution. Okay? So from the lowest equation, you can find X2. When you substitute in the previous, you find X1, you substitute in the previous, you find the next one. So very easy to solve. Okay? So upper diagonal system of equation is easy to solve. Okay, so this gives you an algorithm. So and again, so if believed to 3/5, and then this is very kind of the fastest possible, one of the fastest possible algorithm for solving this system of equations. Okay, so now the algorithm is like that. So so this is essentially proof why kind of it's possible. Algorithm like that is. So first, calculate QR decomposition of A. A is equal to QR. Right? And again, so this is a reduced QR decomposition. Right? And second is, so find, so say call it Z equal to Q star Y. So and this is, if you remember, it is actually projection. So this is at this point we're calculating a projection on the column space of A. But kind of, and third is solve Rx equal to Z for X. So then this is kind of, this is easy. So now, okay, so one thing which to say that actually we reduce QR decomposition of A. So what we did, we used the Gram-Schmidt decomposition to prove the existence of this QR. And it also can be used as a method how to calculate QR decomposition. But turns out it is possible also to calculate this QR decomposition differently and faster. And this is, maybe we'll talk about it, maybe not, but it's kind of, there is another way to calculate QR decomposition, which is called with householder reflections. So this can be done faster than the Gram-Schmidt decomposition. If you use it with faster method, then this is the fastest algorithm for solving these equations. So this is one application of the QR. Now, the most kind of probably famous application, and that's why kind of probably it's in every book, is because it's used to calculate the eigenvalues. I'm not sure if we will be able to explain completely why it works, this algorithm works, but we will kind of at least explain the algorithm, which is extremely simple. Right? And maybe kind of some details, about why it works. Maybe not exactly right, because it seems that you'll need to introduce many additional things, about the eigenvalues and eigenvectors. Okay, so let's start. Yes. And this is also it's also in both books. The varying degree of what is proved. So, okay, so calculation of eigenvalues with your algorithm. So the difficulty is that this is really was a popular algorithm, so it has some many improvements. So let us start with the basic version. So suppose that A is a real symmetric matrix. So in particular, since it's symmetric, it's a square matrix. Okay, so it's a real symmetric matrix. I'm not sure about how important it is real. It's important that it's symmetric, because then we know that it's important that it's symmetric. Then it has an orthogonal basis of eigenvector, and it has real eigenvalues. Okay, so let me just give you an algorithm So the QR algorithm. So first calculate So it's initialization or something. Calculate A is equal to QR. So this is a QR decomposition, QR factorization, and it doesn't matter full or reduced because it's a square matrix. Right? So it's the same. And second, so let A1 be equal to RQ. So just take this QR and multiply it in the opposite direction. Right? So here's the multiplication QR, you multiply it as a RQ. And this in general gives a different matrix A1. Right? So, and after that, repeat. So which means that you do it repeatedly, kind of. So now you apply the same procedure to A1. So in principle, it means that if you have AK minus 1, which is equal to Q K minus 1, R K minus 1, then you define AK is equal to R K minus 1 times Q K minus 1. So the statement is that AK converges to a diagonal matrix with elements with diagonal elements equal to eigenvalues of A. Yeah, so that's it, kind of. So this is kind of the popularity of algorithms maybe because of its simplicity. So you calculate QR decomposition, multiply in opposite direction, get A1. Still, you additionally do the QR decomposition, multiply in opposite direction, and do it until kind of it converges to diagonal matrix. So all of diagonal elements becomes small, and just kind of read off what's the diagonal elements. Okay? So these are eigenvalues. If you want eigenvalues, then you can just kind of calculate it easily. If you know, so if you want eigenvectors, they are easily calculatable if you know eigenvalues. Okay? So eigenvalues is difficult to calculate. You can read it off from, I think, from Q actually. If you read it with a sequence of the Qs. Yeah. All right. Actually, I think that we will stop now. Right? So let's stop now because after that we'll just need to show that this algorithm works, and well, let us do it next time, kind of to talk